Hello, and here we have the walkthrough for the GCSE Combined Science Trilogy Foundation to Chemistry Paper 2. So here we go with question 1. So question 1 says we have tablets to cure indigestion that contain a mixture that has been designed as a useful product. And it asks us to complete the sentence using these words here. So tablets to cure indigestion are an example of, well, it's going to be formulation. Because the definition of a formulation is a mixture that's been designed as a useful product, so that's what it's going to be. Next, it gives us a table of what's inside this tablet. You've got 64 milligrams of sodium hydrogen carbonate, 522 of calcium carbonate, and 68 of magnesium carbonate. Again, the total mass is 654 grams. It's asking us what the approximate fraction of magnesium carbonate is as in the total mass of these substances. So the easiest way to do that would be 654 divided by 68 divided by 654, and we'll see what we come out with. So get the old calculator. So 68 over 654 and 0.1. So that's 1 divided by 10, which will be this one here. Tablet also contains sugar. That's to help the medicine go down. So you need to say something like, to make it palatable, or to hide the unpleasant flavour. Of any medicine. Sodium hydrogen carbonate cures indigestion by reacting with acid in the stomach. If you've got anything that reacts with an acid to make something that's neutral, we call it a neutralization reaction. Next 1.5, the gas is bubbled through lime water. The gas there turns the lime water milky. We need to know what the gas produced is. So the test, we use lime water to test for carbon dioxide, and it should be going milky, so it is going to be carbon dioxide. If it were a squeaky pop, or a lit splint giving a squeaky pop, it would be hydrogen. If it were a glowing splint relights, that would be oxygen, and chlorine would bleach damp litmus. Water is also produced. Which two statements are reasons why water is a liquid at room temperature? Room temperature is around 23 degrees, maybe 24 degrees. So if it's below 100 degrees, it will be a liquid or ice or a solid. So that's one reason. And I'm looking for, here we go, it has a melting point lower than room temperature. So the melting point is 0 degrees. So room temperature is in between the melting point and the boiling point, hence it's going to be a liquid. Next, we're given calcium chloride. We're given the ion that calcium forms, so it forms 2 plus ions because it loses 2 electrons. Chloride ion is -1 because it gains 1 electron. And to join these together, you're obviously going to need 2 single charges for every 1 double charge on the calcium ion, so it's going to be CaCl2, which is this one down here. 1.8, tablets are stored in the glass bottles. Figure 1 shows part of a flowchart for recycling glass. You start off with a waste glass bottle, you then have to crush it, or it gets crushed. You then melt it, or it's then melted and moulded, and that finally gets you the new glass bottle. Question 2 talks about the gases in the Earth's atmosphere today and relates it to other planets and the past. So the first question it asks us, after giving us a table that tells us nitrogen makes up 78% of the atmosphere, oxygen makes up 21%, argon 0.9, and then other gases is an unknown amount, and it's asking us to work out that unknown amount first. So I'll take my calculator first. we'll do 78 plus 21 plus 0.9 plus equals, that gives us 99.9. So these gases are obviously going to add up to 100 because it's a percent. So we'll do 100, take away our answer, and that will give us 0.1. Always use your calculator for these. Next, 2.2 is asking us to plot the data from table 2 onto this graph. So let's quickly have a look back at the table here. Oxygen is 21%, that's what we're plotting. So obviously use your ruler. You guys are going to use a pencil, a sharp pencil that will be provided for you. Make sure you use those. And we need to go up to 21, so 20 is here, 30 is up here, which means each one of the lighter lines represents 2, so we need to be halfway along there. Oops. Make sure the pen works. To there. And you've got to be quite accurate to get the marks here. Brilliant. So that should be 21 again. You can shade it if you want. It's not necessary, just make it stand out quite nicely there. And the next question asks us, what is the name of the gas with the symbol AR? So I would look on my periodic table. If it's a gas, it's probably going to be on the right hand side. This one's a noble gas, which you'll find in group 0, and its name is argon. Some theories suggest that Earth's early atmosphere was the same as the atmosphere of Mars today. Describe the change in the percentage of oxygen from the Earth's early atmosphere to the Earth's atmosphere today. So if we have a look at our table, it started off very, very low. So this looks to be about, I would say, 2 or 3%. So Earth's early atmosphere consisted of only 2 to 3% oxygen. This increased, or this has increased, to 21% in the modern era. So your marking points here are for saying it's increased, and also for using data from the graphs, which I've done here and here. So make sure you use that data. It does specifically say to use values from table 2 as well, so big clue there. Next we've got a pie chart that shows the percentage of greenhouse gases from different human activities. So you've got the generation of electricity, 30%, you've got industry, so factories making things, that's 30%, transport, so cars, buses, trains, planes, 15%, and agriculture, surprisingly high, 25%. But agriculture does release a lot of greenhouse gases. So we need to compare the contribution of each activity to the total amount of greenhouse gases. So I would start by saying that electricity and industry are equal. So that's definitely 1 mark. You could also say that electricity and industry are the biggest contributors. That's the 2nd mark. Transport provides or contributes the least. Agriculture in the middle. So we've described everything there. Oops, sorry, you can't see that. So electricity and industry are equal tops. They're the biggest contributors. Transport provides the least. Agriculture in the middle. So this is probably something that we could look at in the future to reduce our output through agriculture. Suggest one way that greenhouse gas emissions could be reduced. The most obvious way is to use renewable resources. So the way we generate electricity, we need to shift it to a more renewable focus. We could use things like wind turbines, solar power, hydroelectrics. That will reduce these gases given out. Reasons why it's difficult for some countries to reduce: we don't have the infrastructure. So lack of infrastructure, in place. That's the main one. And there might not be an agreement between who should be reducing and who shouldn't, who should and who shouldn't be reducing. Question 3 looks at rates of reaction. So we have a student investigated the effect of concentration on the rate of reaction between sodium thiosulfate and dilute hydrochloric acid. Figure 5 shows the apparatus the student used. So he's got a cross on a bit of paper. He has the sodium thiosulfate and dilute hydrochloric acid in a conical flask. He's observing carefully whilst wearing goggles. Now, sodium thiosulfate and hydrochloric acid react to make an opaque solution. So when the reaction's finished, or when we say the reaction's finished, the student should no longer be able to see that cross through that liquid. The symbol equation for the reaction is Na2S2O3 plus 2HCl goes to 2NaCl plus SO2 plus H2O plus S. So this symbol here represents the thiosulfate, or sodium thiosulfate. Here we have the hydrochloric acid. Next thing in the list, NaCl, that is sodium chloride. This is your sulfur dioxide here, your water, and your sulfur. And it's the sulfur that comes out in a precipitate that makes the solution opaque. We have to plot a graph next. Definitely going to be asked to do this in the exam. So our first reading, 0.1 moles per decimeter cubed of sodium thiosulfate, takes 41 seconds for the cross to disappear. So 0.1, 40, and again each square is worth 2, so I need to be halfway between those. Again, you'll use a sharp pencil. 0.2 goes up to 21, 0.3 takes us up to 20, 0.4 to 10, 0.5 goes to 8, which will be here. And you can see just straight away that this point here might be an anomaly, so I might circle that. And then you have to draw a nice smooth curve. So try and use this part of your hand as kind of the point of a compass. Place your hand on the paper once and draw a nice smooth line like that. The student determines the time to the concentration of 0.15 moles per decimeter cubed. What is the concentration when the reaction is 20 seconds faster? So you're going to have to use the graph for this. So we'll flip the page back over. So 0.15 moles, so which will be here. So halfway in between 0.1 and 0.2. So you draw a line up until that line intersects with the curve that you've drawn, and then you then go across to 30 seconds. So it would have taken 30 seconds for that concentration to complete the reaction. Then it's asking us to work out what the concentration is when the reaction is 20 seconds faster. So if it's faster, it's going to happen in 10 seconds. So pop that down there. That's 10 seconds. We'll follow the line across and it intersects here. I would say, then drop down, and that's 0.40 moles per decimeter cubed. So in here, 0.40 moles per decimeter cubed. If you look on the mark scheme, it actually gives you a range of 0.38 to 0.50. So anywhere within that bound, it's fine, because obviously people's lines aren't always going to be the same. Estimate the time taken for the reaction when the concentration of sodium thiosulfate is 0.6 moles per decimeter cubed. So let me flip back over here. If we have a look at our graph, if we follow it in this direction, this is where it hits the 0.60 mark, and that is around 7 seconds. So 7 seconds. Again, the mark scheme will give you anything from 5 seconds to about 8 seconds. So our reading's pretty good there. Okay, so question 4 looks at crude oil and natural gas. It starts off by giving us this table with the first 5 different alkanes, and it says the percentage of the hydrocarbon present in natural gas from different countries. So as you can see, methane is probably the most common component of natural gas, and as you go down with the bigger molecules you have fewer of them in there. First thing it's asking us to do is work out the mean percentage of propane from countries X, Y and Z. So if this is propane over here, we've got 3 values for propane, so we're going to add them all together and divide by the number we have. So 4.82 from country X, 2.16 from Y and 0.15 from country Z. So add them all together. I always add them all together, press equals, and then I divide by the number there is, and that gives us our answer. If it comes up like this, we press the SD button, and that gives us something we can work with. So I'll write down exactly what I've just typed into my calculator. So 4.82 plus 2.16 plus 0.15 all over 3, and that gave us 2.376 reoccurring, which just means it goes 66666. That's as long as you want. Then I would round it to 2 decimal places, so that's going to go to 2.38. That's 2.38. I'll write that in there. Next question suggests why natural gas from different countries has different percentage of hydrocarbons, because they're formed from different types of biomass, or you could even say plankton. So when they were formed millions of years ago, depending on what organisms died and fell to the ground and were converted into this gas, that's going to change the makeup of the gas. Next, 4.3, complete the sentence. The formula CH4 represents a molecule of methane. So an atom is literally just a single building block, a single carbon atom, a single hydrogen atom, so it couldn't be that. An electron, definitely not that, that's inside an atom. An ion is a charged particle, an atom that's lost or gained an electron, so it's the only one that fits is molecule. 4.4, complete the sentence. The hydrocarbons in table 4 belong to the homologous series of alkanes. So this just means they have similar properties, and there is a general formula for alkanes as well, so that is CnH2n plus 2. So if you know the number of carbons, you can use this equation to work out how many hydrogens you've got as well. Next, so we have some graphs that show how properties vary with increasing size of molecule in this homologous series. So the more carbons you have, the longer the molecule is going to be, the bigger the molecule is going to be. Which graph shows how the boiling points vary. So I know that if you increase the size of the molecule, the boiling point goes up. So I'm looking for a graph that increases, not that, maybe that, not that, not that. Yeah, it's got to be B. So as size of molecule increases, so does boiling point. Viscosity, so this is a measure of thickness or how difficult it is to make it flow. So for example, water has a low viscosity and something like honey or syrup will have a high viscosity. And if we look at our graphs again, I know that the bigger the molecule you have, the more viscous it's going to be. So I'm looking for one that goes up. And again, the only one that goes up is B. So we can use that a second time. Crude oil is fractionally distilled. Fractions with larger molecules are cracked. So crude oil, fractional distillation, you're separating the different length hydrocarbons that make up the mixture of crude oil, but with cracking you're breaking apart large molecules. I know that for cracking you need a catalyst, and distillation, or fractional distillation we should say, does not. We could also say that fractional distillation is a physical process. So you're not making or breaking bonds, you're just separating a mixture, whereas cracking is a chemical process. So you're breaking the bonds inside the chains. So that's a chemical process. That's our 2 marks there. Ethene, can't see that. Ethene is a product of crude oil. Complete the sentence. Ethene polymerizes. So when we polymerize things, we join them together to make long chains. So we start off with a small molecule and join lots of those small molecules together to make a longer, more useful molecule. And to name it, we always start with the word poly, which means many, and whatever it is we're joining together, in this instance ethene, we just have to put inside the brackets like that, polyethene, no problem. 4.9, the production of plastic bags, where are we? The production of plastic bags uses limited resources. Figure 8 shows 2 ways, A and B, of saving limited resources. So we're going to use our object, and then we can either reuse it. So if you have a bag for life, you're going to continually reuse your bag for life every time you go to the shop, every time you remember to take it. And eventually you can dispose of it. So normal plastic bags you just throw away, or you can recycle them, and then they can go back by this process and they can be made into something new. So this part here represents reuse. This branch down here is making something again using the same materials, that's recycling. So A was reuse and B was recycle. So in question 5 we had a student investigated the effect of different catalysts. So a catalyst is something that changes the rate of reaction, increases the rate of reaction without being used up itself, on the decomposition of hydrogen peroxide. So hydrogen peroxide is H2O2 and it breaks down to form water and oxygen. Oxygen gas is produced, as it says here. This piece of equipment is called a gas syringe. It's used for collecting and accurately measuring the volume of gas produced. You have hydrogen peroxide, you have a catalyst, and you can see you've got bubbles of oxygen being given off here. So this shows the students' observations. They used manganese dioxide, potato, strangely, copper oxide and sodium chloride as the different catalysts, and they had a look at how much gas was produced. Obviously you want to get a good amount of gas, but you want to be able to collect it safely. So manganese dioxide would be a lot of people's first choice because it gives you a lot of gas. However, the hydrogen peroxide bubbles up into the gas syringe, and that's going to be dangerous and very difficult to measure. So I don't think manganese dioxide is going to be very good for us. Your sodium chloride, not really enough gas, I don't like that. Copper oxide, a few bubbles of gas, no, that's not very helpful. So I think potato because it was effective, so it gave us a steady flow of gas, but also safe and manageable. So it was safe and manageable. Next, figure 10 shows the gas syringe during an investigation. What is the volume of a gas? So if we have a look here, that's how far the gas syringe has been pushed out, and we can see that it's almost, well, it is exactly halfway between 50 and 100 decimeters. So that's going to be, sorry, centimeters cubed. So that's going to be 75 centimeters cubed. Next, we get given the skeleton of a table, a brief description of an experiment. We have to build a table to put these results in. So for one of the catalysts, the student measured the volume of gas given off every 20 seconds for 2 minutes. So we're going to start off with time. So loads of people forget to put the headings in here, and even more people forget to put the units. So time in seconds, S, you could write seconds, that's fine. And we're collecting the volume of gas. And we're going to measure that in centimeters cubed. We did it every 20 seconds for 2 minutes, so we're going to start off at 0 seconds, then we had 20 seconds, 40, 60, 80, 100, 120. So 120 seconds, that's 2 minutes. And then we need to put these in order. So 23, oh, easy mistake there. So make sure at time equals 0, 0 volume of 0 centimeters cubed of gas was produced. And then we have 23 over here, 42, 59, 72, 80, 88. And it's going to be really tempting to try and put centimeters cubed after all of these, but that's incorrect, and that would lose you the mark. You put your units in the heading of the table, but you never put them in the body here. So units up here, not down here. Suggest why the readings might be lower than expected. Well, some gas could have escaped. There could be a leak, could have been slow putting the bung on, could have had a systematic error. So a systematic error is one which will not be removed by taking multiple repeats, so we're doing something wrong basically. So some of the gas would have escaped is probably the most obvious one, and the one that they look for on the mark scheme. Over here, the student did the experiment with 4 different catalysts, give 2 variables that the student should keep constant. So control variables are the one that we should keep constant. I would say the volume of hydrogen peroxide would probably be the main one, followed by the concentration of the same, so the hydrogen peroxide. You could also talk about temperature. Would be another good one. Must carry out at the same temperature. Okay, so question 6 looks at chromatography, and it starts off by showing us a chromatogram for a particular food colouring, and you can see that the solvent's moved all the way up to here, and the food colouring is separated into 3 different colours. First thing it asks us, how does the chromatogram show that the food colouring is a mixture? Well, you've got more than one colour in a vertical line. So more than one colour in a vertical line. So as the solvent's soaked up the filter paper, it's taken the different component colours of that food colouring up different distances. The distance travelled depends on the solubility of the substance. So this one at the top must be very soluble, whereas this one down here is not very soluble. Student makes some measurements for spot C, so that's the food colouring. It moved a distance of 7 millimeters when the solvent moved 39 millimeters. We need to work out the RF value. That is going to be, RF value is the distance moved by your colour divided by distance moved by solvent. So our colour moved 7, our solvent moved 39, and pop into our calculator. That gives us 0.1795, and I'm going to round that to two significant figures like it asks us to, so 0.18. So because we're dividing a distance by a distance, the units cancel out, so we never have any units. A good way to check you're doing the right calculation is you're always doing small number divided by bigger number, and it should always be a decimal. So next we plan a chromatography experiment to investigate the colours in an ink. So this is one of the 6 markers here. So firstly we're going to put dots of known colours. So these are things that we compare our ink to. So red, blue, yellow, and a dot of the ink on chromatography paper. In your lessons you probably just use filter paper. Place the bottom of the filter or the chromatography paper into water. You need to make sure that the start line is above the water. So what you don't want to do is put your chromatography paper into the water and then submerge your dots of ink, because it's just going to dissolve in the water and it's not going to work. Make sure that the start line is above the water. So let the solvent rise up through the paper. So when the solvent reaches the top, or it's near the top, remove it, let it dry, and then you compare positions of dots in the ink, or dots from the ink, to the positions of the known ink. That should get you 6 marks. Okay, question 7 looks at burning methane in oxygen. The first thing it wants us to do is select the correctly balanced equation. So what we're looking for here is the same number of carbons, hydrogens and oxygens on the left, so this side, as we have on the right. So if we look at the first one, we've got 1 carbon here, 4 hydrogens, 2 oxygens. Over here we have 1 carbon, 3 oxygens. Can't be that one, that doesn't work. Next we have 1 carbon, 4 hydrogens, 4 oxygens. So over here we have 1 carbon, 2 oxygens, 3 oxygens. Oxygens still don't balance, so can't be that one. Next, 1 carbon, 4 hydrogens, 4 oxygens, 1 carbon, 4 oxygens, this is looking good, and 4 hydrogens. So this is probably going to be our one. So we've got CH4 over here, so 1 carbon, 1 hydrogen, 6 oxygens. Here we have 2 carbons. Oh, that doesn't work already, so it can't be that one. Yeah, we were right first time. Next we'll have a look at the effect burning fuel has on the atmosphere. Carbon monoxide, that's produced when we burn things, and that is toxic. So it's an odourless, colourless gas, so it's quite difficult to detect and very easy to kill you. Sulfur dioxide, that causes acid rain, and particulates, they cause global dimming. So they block the sun's light, stop it reaching the earth, so the planet appears dimmer because all the light's being absorbed by these particulates, this soot. The last thing we're going to have a look at is the final 6-mark question about methane, petrol, coal and fuels, and it's asking us to look at this table and to evaluate which ones are better than the others. So just by looking straight away, you can see that methane gives out the most energy per joule per gram, so that's probably the best fuel, so we can start with that. So methane is best fuel as it releases most energy per gram, per G, so let's say gram. You've also got petrol. Petrol is also good. As it's still got a lot of energy, still releases lots of energy, but it's a liquid, so it's a lot easier to handle and transport than a gas or coal. So it releases lots of energy, and as a liquid is easier to transport and handle compared to gas or coal. So methane's a gas, by the way. Next, what else have we got? Coal produces the most CO2, so that's not very good. Coal can also produces sulfur again, which causes acid rain that we saw earlier. And yep, I think that should cover everything. We've made most of our points there, so easy one. Okay, thank you very much.